I'd like to introduce Tyler from Fastly.
Hello, can you hear me? Sweet. Hi, as stated, I'm Tyler from Fastly. You can find me on the internet at @TBMcMullen. Please feel free to argue with me. I am way into that. I will maybe respond if I look at Twitter. I don't know. So this talk claims that it's about isolation and containers, but it's definitely not about containers. I, in fact, will only have one slide that even mentions the word containers. And I'm really, frankly, not qualified to talk about containers for that matter. It's really only about isolation because what we need is to provide operational safety and security. So this talk is about much more about safety than it is about anything else, and of course about WebAssembly as well. What do I mean when I say isolation here? There are a bunch of different ways that we, as like technology professionals, refer to isolation. One is resource isolation. Another one is process isolation. You might talk about fault isolation or software fault isolation. So we have lots of different ways of implementing these different types of isolation. You have processes and containers and virtual machines and so on and so on. But they're all effectively trying to do roughly the same thing to different scales, right? So what I would say is that isolation, and this is not a standard scientific definition of what isolation is, but isolation is really about being able to run some code without it affecting other running code in unexpected ways. Part of that is resource isolation. You know, we'll talk about that more in a little bit and why it's not just about efficient use of resources. Another part, to my mind anyway, is something that sounds a lot like FDIR. Who here is familiar with FDIR? Yes. Every time I give this talk, no one puts up their hand, and that makes me feel like it's a really solid reference. So FDIR stands for Fault Detection, Isolation, and Recovery. This is a concept from control engineering. And is usually referring to monitoring things like thermal signatures and vibrations and oscillations and so on. So it doesn't apply directly, but rather in a much more metaphorical way. I like it because it separates it out the three stages that you need, right? There's detection of a problem, there's isolation of that problem, and there's recovery, right? Detection implies being able to tell when a fault has occurred, which is far less trivial than it might sound, as it turns out. Isolation in our world means being able to prove that when a fault does occur, that it's like its blast radius is limited. And recovery for us means being able to ensure that execution can be restarted and the system continues completely oblivious to the fact that anything has even happened. In a computer program, most of this comes down to two things: control flow and memory. When I say control flow, what I'm talking about is the analysis of the set of possible paths that an execution can take. When I say memory safety, what I mean is the analysis of locations that a program can be storing and retrieving data. If you can work out these two things, you have actually solved most of isolation, most of the problem of isolation. As we'll see, you can actually reduce these to one thing, which is memory safety. And apparently reducing the two to control flow safety is actually still like an open area of research. It's kind of interesting. So let me put this in slightly different terms. What I would say isolation is really about is saying that when I call a particular function, I want to make sure that it can only write to the part of memory that I allow it to, and not to somewhere else. Likewise, I want to make sure that that function can call other parts of the program that I've allowed it to, and not others, to put it in really simple terms. So when you examine what guarantees, if any, you have for control flow integrity and memory safety, what you get out is a fault domain. A fault domain is the answer to the question, what is fucked if this thing blows up? I hope I'm allowed to swear on stage, because I'm gonna. Fault isolation is really about reducing the set of possible faults to something that is knowable and recoverable. For instance, if certain code should not be able to be executed, fault isolation is about being able to prove that it's either not possible or that if it is possible, when it occurs, we can catch it before any harm is done. And so I guess before I go on, I want to talk a little bit about, like, so Till mentioned what Fastly's use case for our isolation, for our WebAssembly-based technology is. And it looks a little bit something like this. we want to isolate every single individual request as it flows into our system. If something goes wrong with one request, we don't want it to actually have any effect, not just on other customers and other users, but on even like the same customer whose software has blown up, right? Which is a much harder problem, as it turns out. So the lifetime of the like isolates, of the like sandboxes that we create is typically under 5 milliseconds. In fact, 5 milliseconds is like on the high end of this. And we're typically doing these about 40,000 times per second. So imagine if you try to apply something like containers to this, or even processes to this. It doesn't really work terribly well. Yeah, so let's talk about processes, though. So this is what a process is, in case you are not aware. That's most of the struct proc in the kernel there. So the question still arises there, because I guess that's not terribly useful. What even is a process? I like to think of a process like this. A process is kind of, it's composed of two parts, right? In user space, you have the memory for the process, and in kernel space, you have its metadata. Right, so that's essentially that struct that we were just looking at. That metadata is not actually directly accessible by an executing process. From a process's perspective, it really is just memory. It's only memory. That's the only thing it knows about is memory. The process has access to its own memory, but otherwise it can't actually interact directly with anything else in the system. And that simple thing is really the crux of process-based isolation. That memory region is by default the fault domain of the process, right? The biggest component of this is a process-based isolation, is this whole concept of virtual memory. So virtual memory uses the hardware MMU and the kernel's VMA subsystem to give each process its own address space, right? This might sound super obvious to everyone here. You're all familiar with this, but essentially what I'm doing here is attempting to get you to think about it in a slightly different way. This allows us to pretend that each process has its own memory entirely. It allows them to share without knowing that they're sharing. So another key part of that is something that probably seems entirely obvious, it's almost as if there's no other way to do it, is that code and data live in the same space, right? If all you have is access to memory, then it seems reasonable that your code for that process also lives in that memory. You undoubtedly already know about this, but process-based isolation works because if the only thing a process has access to is its own memory, and that is also where the code lives, then we don't even have to care about control flow integrity. Does that make sense? Maybe? Okay. So that's an important decision because it ties us super strongly to the safety properties of virtual memory, right? This is another way of saying we don't care what happens inside the process as long as the wall that we build around it isn't broken. So this is why, in my opinion anyway, the Spectre attacks that we saw last year that let us read memory across processes was such a huge deal, right? Because we had this one thing. It was the only thing keeping us safe, and now it's not there anymore, and oh shit, right? Part of the thing that is in the process's memory is an interface to syscalls. So this is essentially the interface with the kernel, right? So calls that affect the process itself or allow communication with other processes in the underlying system. So it's via syscalls that we give processes the ability to interact with other things, which also means that we can do some interesting things with it, right? So for instance, if one process were to mmap a particular file into its memory space, cool. Now that memory is now mapped to a particular file on disk. And another process were to map the same thing. It's actually possible to extend a process's fault domain into the space of another process. Interesting. So one of the ways that we prevent processes from doing these things are actually containers. And containers are actually just processes, for what it's worth. If you have questions about containers, don't ask me. Go ask Jessie Frizzelli, because she knows a lot better than me. Right, so containers are super similar, but we can actually use resource isolation, as well as various other things with containers to limit a process's access to other parts of the system. So what about in-process isolation? What if we wanted to take different pieces of code and put them in the same process, in the same address space, and stop them from actually affecting each other? Well, the first question is why? Why would you even be interested in doing something like that? It seems like a terrible idea. The answer actually comes down to overhead and efficiency for the most part. So if you imagine like, if you have two different processes and they're isolated from each other, the only way that they can interact is via the kernel at that point, unless you're like mapping memory between them, but in that case, you're still using the kernel to make that mapping happen. So if you wanted to communicate from one process to another, you would say, okay, I am in process 1 and I want to send a message. And you will switch over, you'll do a context switch into the kernel, and the kernel will say, okay, I received your message, great. And then process 2 will wake up and it'll say, I would like to receive a message. And it context switch into the kernel, and the kernel says, okay, here's your message, and it context switches back. Yeah, so you kind of get the point here. Like this can actually be quite a bit of overhead. So the nice thing about trying to do this, if you were able to do this in some way inside of the same process, inside of one process, sharing information and communicating between these quote-unquote processes would look much more like call, right? And so my theory here is that, or my theorem is that high-performance systems with many small tenants and strict latency requirements may find that VMs, containers, and even processes are all far too heavyweight for what they would like to accomplish, right? So what are we to do? Let's talk about WebAssembly. I will skip the majority of my WebAssembly intro because I feel like you all know it already, and that seems silly. But WebAssembly is the first. I'll talk about WebAssembly from my perspective, like why it's interesting to me. WebAssembly is the first fast, multi-language, retargetable, safe, intermediate representation that we have ever actually agreed upon as a community. I can't stress like how important and different this is, right? We as a greater programming community have never had that before. It's never happened. Like probably the closest we got was like JVM bytecode, and no one liked it. It's actually quite exciting. I will skip my explanation of what a WebAssembly is. So some of the key differences, though, between like, what we expect from a modern computer versus what WebAssembly provides us, like the biggest one probably is that pointers are 32 bits, as Lynn talked about at length earlier. Another important one is that there is relatively little non-determinism in this, unlike basically everything else about your computer. One that's weird that can trip people up quite a bit is that null does not equal 0. So when I was attempting to write my little demo that I will show you in a little bit, I was like, oh, I should show them how, like, if you do a null dereference, it'll blow up, but it'll be safe. And then I realized that it won't blow up because null is totally fine. So one of probably the biggest one, though, that I think is interesting is that code is separate from data. And that's probably the biggest thing that makes it different than like other sorts of like process isolation. So if you recall, a process attempts to take care of both control flow safety and memory safety with one fell swoop using the virtual memory system. But WebAssembly is different, right? The actual code for a WASM execution is kept separate from the memory. Like the code can't actually access itself. And one of the goals of that is to constrain that fault domain. So the code is actually kept safe, and it can actually be reused after an error. Right, so we don't have to throw away the entire thing. We can actually like, oh, cool, like it had an error. We can, like the code is still fine. It's totally cool. There are some interesting implications of that, right? So that means that computed go-tos are kind of not going to happen because you have no way of like talking about the address of a piece of code or like an operation you want to jump to. It doesn't make any sense. Function pointers require shenanigans, essentially. Like function pointers aren't really pointers anymore. They are, in fact, indexes into a table. And as I mentioned, like crashes don't mean throwing away the code. Okay, so if we can compile our code to WebAssembly and we can get the safety that we need, so it turns out, obviously, as you all know, like Clang and Go and Rust and TypeScript and others now have relatively mature WebAssembly backends, which is pretty exciting. But that's really only half the story, at least for our side of things. Like we still have to find a way to compile that WebAssembly into native code and make sure it's like actually fast, right? So what we've been working on is an ahead-of-time compiler and runtime for WebAssembly, which as Till mentioned. So we take that WebAssembly code and we turn it into native object code as part of that ahead-of-time compilation. And the way that we're doing that is crane lift. the project that Mozilla was talking, or the folks from Mozilla were talking about earlier. We've been contributing to it and using it for quite a while now, and it's like come a long way since we were first looking at it. You can kind of think of CraneLift as like a smaller, lower level version of LLVM specifically made for WebAssembly, but you can actually use it for other things as well. So we've developed a decent amount of code inside CraneLift and on top of it, which ends up implementing that isolation scheme that I've been talking about, which is pretty exciting. One of the neat things about this to me is that running that code that we have ahead of time compiled via CraneLift just kind of looks like that. You just kind of DL open it, and there's a little bit more to it, but effectively at its core, that's really what it is, right? It's just a normal shared object. So how do we make it fast? I cut down some of the interesting examples of this from my talk, but one that I really enjoy is the bounds checking discussion, right? So particularly bounds checking can be incredibly expensive for programs. I read several papers about this before we were working on this, and it turns out that like you will typically see in like traditional code, not WebAssembly, anywhere between like 2x and 50x slowdowns if you try to implement bounds checking inside of like a standard C program. It's pretty gnarly. So WebAssembly makes this better. It makes it like significantly better. So let's see why. So going back to like the concept of virtual memory, one of the key parts of virtual memory is that it can have holes in it. Why does that matter? Well, let's say I want to write a bunch of data into my memory. Let's say I want to write a block of data that looks roughly like that, right? So I want to write right across all these holes in my memory. If I wanted to bounds check this to make sure that it's not actually going to do anything, it's not going to try to write to anything that is like not actually swapped into my process at this moment, I in fact don't just have to check both ends. I actually need to check everything along the way. I need to find where exactly all the holes are and check to make sure I'm not actually about to write into something that doesn't exist. WebAssembly uses a concept called linear memory. Linear memory is interesting because it doesn't have any holes, and it in fact grows upward and only upward. So that means if we were to take that same block of memory that we want to write and drop it into our linear memory, what do we have to do to bounds check this? In fact, all we need to do is bounds check the end, 1, right? So that's pretty cool, and that makes things a lot better, but we can actually do even better than that. Let's talk about bounds check elision. And I'm going to talk about this, however, you should actually talk to Dan Goman about this because he's the one who implemented the bounds check elision inside of CraneLift, and so I'm really just stealing his thunder here. So in a naive setup, this one little line of code might expand to something like this in WebAssembly, right? So I have my array. I keep looking to my left, expecting the slides to be there. I have my array here, and I want to write to a particular address in there. And so that'll expand to roughly that, right? So I push the 0 onto the stack, and then I store it at a particular offset. So in a naive setup, let's say we have just our linear memory. That's all it is. There's nothing special about it. It's just a block of memory. That code might actually expand to something that looks a little bit more like that. So this is the part of the talk where I'm going to put a bunch of assembly on the screen. You're welcome. So in this case, what we do here is, well, first of all, we compare the bound that, against, I'm sorry, how does this work? Right. So, we're comparing RAX, which in this case I'm assuming is the address of the base of that array. I'm going to compare it against the bound of the program, right? What I know to be like the highest address in memory. And if it doesn't meet that bound, if it's like actually beyond it, then I will throw a UD2, a sig-ill, which the runtime will then catch, and we'll be like, oh, okay, cool, I caught it, everything is safe, but you're still out of bounds, so like this process is dead, it's fine. Right, so then I will check to make sure that the actual offset that I am looking for from that array is actually in bounds as well, right? And so from there, we finally get to the actual instruction, which is just putting a single 0 into memory. So what can we do to make this a little bit better? All right, so if we take that linear memory and we add a guard page onto the end of it, just one guard page, just a 4 kilobyte guard page. What does that get us? Interesting. So what that would get us is that given that we know that the index of 17 is within 4 kilobytes, of the end of the base that we have checked, we can actually skip checking that offset entirely, right? As long as we know that the offset, which is a static number, it's known at compile time, as long as we know that that is within 4 kilobytes, then we check the base pointer, and it's in bounds. Like that's all we have to do, and we're good, right? And if we attempt to go beyond that and hit that guard page, we'll throw a SIG-SAG V, which will again be caught by the runtime, and everything is cool. The neat thing about this is that if I want to write a bunch of things to memory, right, this actually lets me amortize that and check only the base pointer, and then write a bunch of things to memory. All right, so we have our linear memory. We have our 4 kilobyte guard page. What if we make that 4 kilobyte guard page a little bit bigger? What if we make it about 1,000,000 times bigger? So specifically, we reserve an amount of memory that is exactly the maximum size that a WebAssembly program is capable of addressing. Remember that WebAssembly addresses are 32 bits, so that's not actually a crazy thing to do, right? This is actually only 4 gigabytes of like a relatively massive virtual memory space, right? So, okay, so what can we cut it down to now? All right, so we still have our 1 address, and we can cut it down to no bounds checks. And that's a pretty cool thing that 32-bit space and like the design of WebAssembly can get you, right? This is the thing that lets us get it to be very close to native speeds for a lot of the code that we compile. Okay, enough assembly. How about a live demo? Yeah, live demo. This is totally going to go well. All right. So if you're not familiar with this, this is Terrarium. So Terrarium is the demo of the WebAssembly isolation technology that we've been working on for quite a while now. And the team that built Terrarium with me is sitting right over there. You should go say hi to them afterward. But so, wanted to think of a couple things that we could show off here that would kind of show what we're talking about and why this is interesting. So first, before we get to that one, I'll show something kind of interesting here. Like what happens when a program faults? Oh, that's not cool. Also, thank you to Mozilla for the fact that we were graciously allowed to use the WebAssembly Studio UI. It made the whole project a hell of a lot easier, so thank you for that. Okay, so the C program that we have here, this is an IDE. What we're going to do is we're going to build and deploy this. What it will give us is it will give us a URL. We can then go hit that URL, and whatever is in the run function here will be run as soon as that happens, and we'll get some output from it. So in this particular case, what we do is we make a pointer called uh-oh, and tell it to be -1, totally valid pointer. And then we attempt to dereference it into a character called boom. So let's see what happens. So first of all, let's hit build and deploy. Here we go. It's building, it's deploying. It's working, I promise. Right, generating machine code. It's calling crane lift right now. Don't do this to me. All right, okay, so we got a URL out of it. All right, so what's going to happen? All right, so we click that, we get here, and what we see here is not the prettiest error code, but it is exactly the error code I was expecting it to be, so that's good. So what we got here is a WebAssembly runtime error. And in this case, in our fault details, we can see that, first of all, fatal is false. And that's great news. That means that this error was caught. And it means that the process that is running this piece of WebAssembly code is totally safe. Nothing happened that was like unexpected. And specifically what happened here is we got a heap out of bounds error. And we get some other details that are less interesting. Cool, okay. So that's great. Let's do something else with it though. Let's see, how about an image processing example? So when I said that this was like near native speeds, I actually meant that. So we're going to embed libjpeg, thank you Frank, into a WebAssembly program, and we are going to run some image processing examples every time this thing is hit. We'll see what we see. This is what I get for running on the cloud. All right. All right. All right. And so we'll get some examples here that Frank lovingly put in here. And so, okay, what will we see if we take our image and we manipulate it? All right, so here the image has been resized to 640 by 360. And I think it's worth noting that this is doing a significant amount of processing for each of these images. And every time I run this, it's actually creating a new WebAssembly instance and responding and loading libjpeg every time. And that's pretty cool. I'm pretty happy with this, right? So this is what I mean when it is near native speeds. And yeah. Hey, live demo success. All right, so review. Isolation is like an incredibly important thing with the way that we build programs today. It's incredibly important to the way we build them and the way that we do computation in general today. It's just kind of an assumption that I think a lot of us don't really think about very much, especially when it comes to multi-tenancy. But even for like the reliability of trusted systems, isolation is just as critical locally as it is when we're talking about like distributed systems. WebAssembly is a pretty awesome way that we now have of implementing isolation, of implementing software fault isolation, and gives us an entirely different way to scale that isolation, a way that we have never had in the past, and that's extremely exciting. So thank you very much. Good night.
All right. Thank you, Tyler. And congratulations on surviving the demo gods. That was awesome. Well, that's it for our talks, but we have plenty of time to hang out here. You can talk to Tyler, talk to Till, to Lynn, talk to each other. We still have some soda and wine left, so feel free to drink that up. And we got to get out by, call it 9:45, so feel free to socialize. Thank you.